Okay, thank you very much for joining this webinar on how wind technologies can help deliver climate change targets. This webinar is part of a really exciting series being run by ETP over the course of the summer through their Energy Innovation Emporium, all in the run-up to COP26. So if you've not registered for the other webinars in the series, please do log on to the ETP website and do so. There's some fascinating presentations and speakers over the course of the summer. This particular webinar is going to focus on the wind energy sector and what it means in the context of the UK and its ambitions for net zero, how wind in combination with hydrogen can solve some of the really difficult to decarbonise sectors, and an exploration of some of the challenges to deploying and integrating this wind energy as well. And we're really fortunate to be joined by guest speakers from Scottish Gas Network, so Lorna Archer, and the Ocean Energy Research Association, all the way from Canada. So thank you for the early start, Alistair McLean. So I'll just go through a brief introduction about some of the organisations who are taking part in this webinar, and we're going to do a Q&A session at the end, so please feel free to put questions in the chat as you go along. Don't worry about remembering them, put them in the chat, and then we will come back to them and answer them at the end between us. So first off, briefly to introduce ETP. So ETP is Scotland's research pool for energy, and it's an alliance of 13 Scottish universities who all are engaged in world-class energy-related research, development and demonstration with some really cutting-edge facilities. So one of the main kind of business-facing programs as part of this is the KEN program, the Knowledge Exchange Network, which provides funding to Scottish SMEs to support low-carbon technology development in collaboration with academia. So until very recently, I worked for ETP fulfilling that BDM role, but my colleague Steph Mann has picked up that mantle and is now looking after the business development manager role for the wind theme. So if that sort of support sounds of interest to you, I've left her email address on the screen, but please feel free to get in touch. So to briefly introduce the speakers, and Lorna and Alistair will, I'm sure, introduce themselves more thoroughly towards the end, so apologies if I've not done you justice here. But I'm Alex Loudon. I'm a Senior Technology Acceleration Manager at the Offshore Renewable Energy Catapult. So I'm responsible for a lot of ORE Catapult's work engaging with small and high growth companies, including more structured programs of support like our accelerators and innovation challenge programs. And I'm joined today by Casper as well. Casper Stefaniak is a strategy analyst at ORE Catapult who leads on innovation road mapping for a program we do with the KTN called the Offshore Wind Innovation Hub. And he's also really acutely involved with a lot of our kind of activity looking at future scenarios for net zero and also on hydrogen. So for those of you who don't know the Offshore Renewable Energy Catapult, we are the UK's flagship research and technology centre for offshore wind, wave and tidal energy. And we're part of a network of catapult centres, all created to deliver a step change in the UK's innovation capability and capacity, and really to encourage the propagation of low TRL technologies out into high TRL so they can have a really material impact on their sectors of target. So we're a national organisation with our headquarters in Glasgow and our main facilities located in Blyth in North East England, but we've got offices and kind of research hub collaborations up and down the country as well. So to get into the meat of the topic for today's agenda, I thought it would be really useful to explore a little bit about what does net zero mean for the UK, and why might hydrogen be important in telling that story. So net zero means that by 2050, which is the target the UK has signed up to, we as a nation, we must on average across our whole economy emit zero emissions. That doesn't necessarily mean that we won't emit any greenhouse gases, but any that we do emit must be offset by sequestration of greenhouse gases in other sectors or technology areas. So on the left-hand side are just some of the things that this might mean for our economy. And I think it's probably quite important to stress that nobody really knows exactly how we're going to get there, although there's some really good work being done by the likes of the Committee on Climate Change to try and identify roadmaps. But these are just some of the changes we're likely to see. So offshore wind, which is largely the subject of today's talk, we're at just over 10 gigawatts in the UK just now. But by 2050, we might need 75 to 100 gigawatts of offshore wind, not only to meet the demand as we see it today, but we could see up to a doubling in electricity demand as other sectors become electrified as part of their transition towards being net zero. Hydrogen production we'll see as a running theme today is going to increase dramatically. Low carbon heat and transport is a really big challenge. But then as well, I think we're likely to see things like huge amounts of increased forestry plantation as part of that sequestration of carbon emissions for sectors where it's impossible to reduce emissions to zero. And I think we're going to see more social changes as well, like diet through reduction in some of the highly carbon intensive food types. And so I think this slide kind of indicates some of the scale of some of these different sectors which I've mentioned. And on the left-hand side in the bright blue are areas that the Offshore Renewable Energy Catapult are currently looking at in some of our projects and programs. So the obvious one is electricity production and transition to increasing the amount of offshore wind dramatically. And moving away from things like oil and gas extraction and coal mining. But I think as we look to the future, we need to think in a far more integrated way about how that interacts with other sectors. So on this slide, we can see a much bigger box of areas that offshore wind and some of the research that we're doing has the potential to impact. So road traffic, obviously, the electricity from offshore wind is eventually going to be used largely for charging of electric vehicles and things like that. And some of these challenges are more or less easy to address than others. So there are things that can already be done using electricity are quite easy to decarbonize because you can move from using gas or coal produced power to renewable energy. However, there are a lot of sectors at the moment that simply don't use electricity as their source of energy. So some examples of that might be long-haul freight transportation, where the energy density of batteries remains a significant barrier to reducing the emissions of be it lorries or shipping or trains for freight. Likewise, heating in high population density areas is another big challenge. Gas boilers are pretty much ubiquitous across most of the housing stock, but especially in urban areas where technology such as heat pumps is unsuitable. So again, electrification becomes very, very challenging. And then there are kind of industrial sectors that require very, very high heats. And again, this is very difficult and inefficient to achieve with electricity. And so we need to start thinking much more holistically, not only about what offshore wind and electricity can do, but how we can convert that electricity into other energy vectors, which can help decarbonize some of these really difficult to achieve areas. So to briefly address those, hydrogen can be carried at quite a high density, and through refueling, which is much more alike filling up your car with petrol, it unlocks the ability to carry high masses, longer distances. There are projects underway, and I think Lorna might touch on this later, to use hydrogen as part of legacy infrastructure like the gas networks through relatively minor modifications that can, so using hydrogen boilers instead of natural gas boilers. And likewise, hydrogen can be burnt, which can generate much higher heats for some of these industrial processes, like smelting, for example. So I think we can conclude that hydrogen is going to be pretty useful and we're going to need more of it. So is offshore wind the right source of energy to produce that hydrogen? And should we just be using electrolyzers and offshore wind energy to produce all that hydrogen? So it's probably useful to take a bit of a step back and look at how the offshore wind sector has changed over the last couple of decades. It's still a relatively immature sector in purely age terms in the scheme of the economy. The first offshore wind turbines in the UK were installed in 2001 in Blyth, near where our facilities are, and they were 2 megawatts in size. Now, this graph shows the maximum turbine size installed on a given year, and we can see that just the year after next, in 2023, we're going to be up to 15 megawatt turbines being installed, which is a huge increase in the size of these turbines producing electricity. In 2000 it was 2 megawatts. In 2010 it was 6 megawatts. In 2020 it was 10 megawatts. What's it going to be in 2030? There have been people who have made bets on this in the past, and they've always come up short. So is it going to be 20 megawatts? Is it going to be even bigger? We don't know, but I think the only certainty is that it's going to be bigger than what we're expecting. And I think coupled alongside this is that the performance of offshore wind is improving all the time as well. So the chart on the right, it was produced by the Crown Estate in their operational report last year. And it shows that the green bars are the capacity factor, which essentially means the proportion of the time that they're running at full power. So a capacity factor of 50% for a 10 megawatt turbine would mean that on average they were producing 5 megawatts. And you can see this steady uptick over the last decade and a half in the capacity factor to a point where last year the average capacity factor was 45%, which is a far cry from the kind of 20 to 30% that we typically see for onshore wind. And it just goes to show how much energy we can produce from offshore wind. And this is down to a number of reasons. So we're improving how we operate and maintain these turbines all the time, which can only improve their performance. And the turbines are getting bigger, so they're taller and interacting with higher wind speeds in the atmosphere. And they're getting further from shore, where typically wind speeds are more steady and reliable than they are either onshore or close to shore. And whilst wind will always be an intermittent energy source, improving capacity factors makes it significantly easier and cheaper to integrate into the grid. And on this graph, we can see that cost reduction in action. So this graph shows contract for difference strike prices awarded to UK wind farms. And the contracts for difference is the mechanism that the UK uses to award support to consented wind farms and provide them with a route to market. So back in 2016-17, the first contract for difference auctions that were run, we were seeing wind farms bidding in a competitive way at around £150 per megawatt hour. Whereas in the latest auctions, we were seeing prices beneath £40 for wind farms to be installed over the next few years. Now, for context, the current wholesale electricity price typically sits somewhere between £50 and £60. So wind farms which are going to be being built in 2023 to 2027 are cheaper than the average price of electricity currently. So it'll be, instead of attracting a subsidy from the taxpayer, it will actually be paying money back to the taxpayer's purse and reducing energy bills. So this all really helps to kind of paint a picture of why offshore wind needs to be the backbone of our future energy system, and why the scale needs to increase so much to produce electricity, not only for things like electric vehicles and heat pumps, but also for hydrogen to help with some of these difficult to decarbonize sectors. And so, I think this last section has painted a pretty good picture about offshore wind, but realistically, how much can we install? You know, it's still a challenge to get it all in the water. So how much could we have? And this chart shows the UK's current pipeline. So at the moment, we've got around about 10 gigawatts of operational offshore wind in UK waters, with a further 4 gigawatts under construction. If we add to that the 12 gigawatts of consented offshore wind and a further 25 gigawatts under development, that takes us up to about 51 gigawatts in total. For context, our national target for the year 2030 is to install 40 gigawatts, which is the dashed line across your screen. So with the amount of sites that are in consideration or under development at the moment, we've got enough to meet that target. But it's still a far cry from some of the numbers that I presented on the first slide of 75 to 100 gigawatts. It's worth mentioning that we're expecting the Scotland leasing round to add an additional 10 gigawatts to the development pipeline, and that will be taking place later this year. So we'll probably be up to around 60 gigawatts, but still not far enough. And so this just kind of brings all that information together to show how the reduction in cost is coinciding with the increasing capacity of offshore wind installed in the UK. And this splits it out nicely between the black line, which shows fixed bottom offshore wind farms, which have more traditional foundations, either piled or drilled into the seabed, compared with floating offshore wind farms, which is the brown line. And these are use floating substructures and can work in much deeper waters, and therefore potentially unlock higher wind speeds closer to the shore, which is really exciting. So that's still a maturing technology, and that's why you can see that the LCOE, or levelized cost of energy, is a bit higher, but that's going to rapidly come down and become cost competitive with fixed bottom offshore wind over the next couple of decades. And so in the context of the global pipeline, the top chart shows the amount of offshore wind we're expecting through our analysis to be installed each year. And the bottom graph shows cumulatively how that stacks up. And at the moment, the UK is the largest offshore wind market in the world by installed capacity. However, we're going to be outstripped by China very, very soon on that. But you can see that across the whole world, the annual installed capacity is going to increase and increase and increase. And the reason for the slight drop off after 2030 is really because of lots of countries, just like the UK, have really ambitious targets for 2030. So there's going to be a big push towards the end of this decade, but then a more kind of steady growth afterwards. So out to 2030, we're expecting a compound annual growth rate of around 20%, which is absolutely enormous. And so at that point, I'd like to hand over to Casper to talk through some of the challenges in realizing this vision. So over to you, Casper.
Thanks, Alex. So this moves us to how our energy system will look like in the future. It's going to be significantly different to how it is right now. We will move from the fossil fuels to renewables and nuclear from around 48% in 2019 to 75% in 2050. The installed capacity will at least double from 111 to somewhere around 278, according to energy scenarios by National Grid. This means that interconnectors and hydrogen support will play the key role in supply side flexibility. A bit more on this on the next slide. It's also worth noting that by 2030, the immature by age technology, which is offshore wind, will be the biggest single source of installed generation capacity. Having this much renewables means that we will need quite a lot of flexibility in the system. And in the future, it will be provided on the electricity side and on the natural gas and hydrogen system flexibility. On the electricity side, we will have supply side flexibility. This will be given by large-scale electricity storage, interconnectors, so import and export electricity from Great Britain or connections to other markets, and other dispatchable thermal generation. On the demand-side flexibility, we'll have various demand-side responses, both from transport, residential, industrial, and commercial. So examples of this are smart charges and vehicle-to-grid, smart home energy, and commercial heat pump flexibility. Quite key in all of this will be hydrogen, so both through the blue and green hydrogen as electrolysis. So let's move on. This is a graph that shows how a future energy system dominated by offshore wind could look like. In an energy system like this, we would experience few integration challenges. We will need to take care of balancing for short time frames, but also for long time frames. We'll need to deal with decarbonizing heat, cargo transport, and the maritime sector. So the challenges will be quite big, but there are surely ways in which we can work around to overcome them. Maybe let's start with how do we transfer electricity at the moment. The transmission of electricity right now is done through HVAC. This is a form in which power is generated by wind turbines and delivered to an end user. It is a cost efficient for short distance transmission and is a traditional system in the UK. But as we will be moving to the wind farms that are located farther offshore, the HVDC systems may offer cost advantages over the whole lifetime. They're currently used only for point-to-point connections. And HVDC give not only cost benefits, but there are a few others like lower losses. The HVDC line offers better voltage regulation. There is a greater controllability. There's also possible for interconnection to the grids. Dogger Bank is the first project in the UK that will build 2 HVDC converter stations. This wind farm is being developed by SSE and Equinor, and we're expecting it to be built in 5 to 6 years. This graph shows how the electrical network can look like in 2050. So with the current approach in the status quo, we can expect a capex of around £29 billion. Total number of assets will be 330 and 105 landing points with multiple HVDC point-to-point links and HVAC. Not really much integration of the assets. If we apply the integrated approach in 2030, we could reduce the capex by 7%, the number of assets by 40%, and the number of total landing points to 60. This would be mostly done because of the more strategic location of the assets, including meshed HVDC substations and interlinks. If we apply the integrated approach from 2025, the capex cost would go down to £23 billion. So I think that would be just minus 80%, not minus 189%. That would be great. The total number of assets would be reduced by 70%, and the landing points would go to only 30. Again, this would be mostly done by even bigger interconnection, meshed HVDC substations, and links. In this study, you can see some different alternatives to how wind farms are connected right now. Radial is an incremental connection of offshore wind projects to shore. Hub means that we would have a strategic connection of offshore wind clusters to shore. And integrated energy neutral, we could consider offshore wind to offshore wind connections. And in fully integrated, we could have an unconstrained cross-border electricity trade with EU-wide security. An example such a connection, it could be the Dogger Bank. So the net benefit of the integrated system is around £500 million from reduction in offshore network cost. If it, in the non-integrated scenario, we would have one connection with the wind farm and then an interconnection with Norway. In an integrated one, the interconnection would just go to the wind farm, saving quite a lot on infrastructure. Integrating electrical infrastructure could bring quite a lot of savings. It's been assessed that it could be from 35 billion to even 70 billion pounds. Full integration would also include oil and gas drilling, and the synergies could bring reduction in OPEX. Those synergies include common onshore O&M base and reduction of onshore personnel required. Potential use of shared service operating vessels for many projects, synergies for deploying maintenance campaigns with just one single mobilization cost, and potential improvement of accessibility with SOV higher access capabilities. Interconnection definitely supports balancing. As you can see on this chart, the requirement for energy storage is significantly lower with an unconstrained interconnection. The next idea on how to deal with even bigger methods are energy islands. This is an idea that's being brought forward by the Danish government at the moment. They want to establish 2 large-scale offshore wind farms projects, or so-called energy islands, by 2030. They've been agreed already by the parliament, and the environmental assessment is being procured. There would be 2 wind farms. There would be 2 energy islands. One would be in the Baltic Sea, the other one in the North Sea. The initial capacity would be 2 gigawatts and 3 gigawatts respectively, with a potential scale up to 5 and 10. There's an possible integration of power to X on the island, so some of those could be used directly to produce hydrogen. Which moves us to the hottest topic of the past year probably, which is hydrogen. There's been quite a lot of discussion around it. As Alex already mentioned, there are some sectors that can be electrified, and it offers ways to decarbonize a range of different sectors. And this would include long-haul transport, chemicals, and steel. It would essentially play the same role as oil and gas play in the current energy system. It would strengthen our energy security and increase flexibility in power system. Additionally, in the UK, it can help to secure a future for the extensive skills and assets of our oil and gas industry, where we have quite a lot of oil and gas platforms and pipelines in the sea in terms of infrastructure, but also a significant amount of labor and skills in this sector that could be transferred to hydrogen. Quite sure that you've heard quite a lot about hydrogen, but I just wanted to clarify what those different colors mean. I think the 2 most commonly heard are green and blue. So green is a renewable hydrogen production based on electricity. The electricity source can be wind, solar, or hydropower. The technology that's being employed is water electrolysis. There are different types of electrolyzers. The 3 most commonly talked about are PEM, AIL, and SOIC. There are no emissions involved, And the other terms that are used to describe this hydrogen is clean, zero carbon, or carbon neutral. Blue hydrogen is fossil fuel-based hydrogen. The technology employed is natural gas reforming and CCUS. It doesn't capture all the emissions. Currently, the capture rate is estimated that it will be around 90–95%. That's why it's not a zero carbon hydrogen production, it's low carbon. At the moment, hydrogen is used in several industries. So there are already existing hydrogen production methods that employ natural gas, brown coal, and black coal, and those are gray, brown, and black hydrogen, respectively. The biggest challenges in developing hydrogen economy are on this slide. So first is the source of hydrogen. At the moment, around 120 million tons are produced each year worldwide, and most of it is generated from fossil fuels. There is no significant production from renewable energy sources, and the majority of the hydrogen today is produced and used on site in industry. The production of ammonia and oil refining are the prime purposes. Second is the cost. Currently, the zero carbon hydrogen is more expensive than the fossil fuels based. However, in our recent study called Solving the Integration Challenge that we did together with Offshore Wind Industry Council, we've seen that green hydrogen from offshore wind could cost less than blue hydrogen and the black one by 2050. With accelerated deployment, it can be competitive with hydrogen as early as the 2030s. The third challenge is related to the markets. It's not only about the production, we also need a significant amount of demand and investment. Developing hydrogen economy will not only require research into electrolysis technology, but also fuel cells and use cases. So that's why a national strategy is really needed, an integrated approach to deliver accelerated deployment, supported by appropriate regulation and policy, targeted R&D, demonstration and large-scale validation of developments. A bit more on the cost. On this chart, you can see the system cost breakdown of an electrolyzer by 2050. You can see that the majority of the cost reduction appears by 2030. And the biggest driver of the cost reduction is electricity used to produce hydrogen. As you know, the cost of offshore wind will keep on dropping down, and we believe that with the cost plunging, we'll be able to reduce the cost of hydrogen as well. Most importantly, technology is an essential means of reducing electrolysis costs. So probably the first 1 gigawatt of installed capacity will be expensive, but as we move forward, the costs will keep on dropping down. The good news is that we've already did that before with offshore wind. Another advantage is that UK has a strong leadership in academia and industry to build on to develop this economy. A bit more on the supply chain side. As I've mentioned, it's not only about the production. There are numerous sectors in which it could be used. Going for distribution and transport, storage, and conversion of other fuels. We'll need to develop use cases for mobility, for industrial energy, for domestic energy, and for industry feedstock. That's why in Energy Catapult, we are developing different projects that try to incorporate that. Two of them are Milford Haven Energy Kingdom, where we're trying to investigate how a local hydrogen energy system could look like in the region. And the second one is H100, which Lorna will present right now. Thanks, everyone.
Perfect. Thank you so much for that. Hopefully I can get my screen share working okay. There we go, that should be that ready for everyone. So thank you very much. Two really good presentations so far, and a really good in terms of setting the context of what I'm now going to speak about, which is the H100 Fife project, and really looking at this as a case study for offshore wind to hydrogen for heat. So this is a world first demonstration of 100% hydrogen to homes network, which is aiming to prove the innovation of offshore wind to hydrogen and paving a way for decarbonisation at scale, and importantly in a form that meets the wants and needs of the customer. So for anyone on the webinar that doesn't know who SGN are, we are a gas distribution network company operating across Scotland, Southern England and Northern Ireland. And our Scotland network distributes gas all across Scotland to 75% of households. And we also have our remote areas which are supplied through our Scottish independent undertakings. So just having a look at the hydrogen context and what's going on with the gas networks. SGN's medium to long-term net zero strategy is to replace natural gas with hydrogen gas, as well as other green gases, enabling the decarbonisation of the gas network's energy supply. And then moving towards greener solutions, the gas networks with their infrastructure can really offer a practical, low cost, low disruption solution for the decarbonisation of heat, and whilst retaining the use and the benefit of the UK's extensive gas networks. So H100 Fife itself is widely acknowledged as a critical demonstration with national significance in evidencing the role that hydrogen can play in decarbonising heat, and is aligned with the Gas Goes Green programme and the gas quality decarbonisation pathway. So there's already a huge movement in this space in terms of collective and collaborative support across the gas networks to decarbonise. And if I was to explain the project in a nutshell, really it's an SGN-led project that seeks to validate the supply, storage and distribution of 100% hydrogen through a new gas network to customer homes for heat, and incorporating offshore wind for hydrogen generation. There we go. So whilst this demonstration trial is being proposed, this is not come out of nowhere. It's been built on an extensive hydrogen evidence base, which this slide alludes to. And there's been a huge number of project partners involved in this and collaboratively with the gas distribution networks, as I've alluded to. And this has really brought together this collective research base that's provided us with the evidence that we need to proceed to the demonstration phase of a safe hydrogen trial. So on the next slide, I've got an animation to show you. It's just about 3 minutes long, but really sums up the project nicely, and then we'll dive into some of the detail.
H100 Fife is a national research project led by SGN that aims to deliver a 100% hydrogen gas network, demonstrating both the Scottish and the UK's commitment to taking action in the global fight against climate change. SGN is one of Great Britain's 4 gas distribution networks, delivering gas to almost 6 million customer connections across Scotland and southern England. We are working towards replacing the natural gas in our pipelines with gas that produces no carbon emissions by 2045, helping to deliver the UK's net zero target for 2050. Our planned H100 Fife project in Leavenmouth builds on an extensive evidence base for hydrogen and aims to be the first 100% hydrogen to homes zero carbon network in the world, showcasing the UK's low carbon future. Hydrogen gas will be produced through a process called electrolysis, using green electricity from an offshore wind turbine to split water into hydrogen and oxygen. The hydrogen is then stored in secure tanks before being transported through our network to customers. We'll start by connecting 300 homes to hydrogen, although our new network will pass by 1,000 homes. Customers will be able to interact with hydrogen appliances at a demonstration facility before choosing to swap from their natural gas supply to our new hydrogen network. Once it's up and running, we'll be able to measure the technical, social and commercial performance of the world's first fully operational 100% hydrogen network. Proving the case for hydrogen may well be a game changer in how we build a carbon-free economy. It will make the most of our national gas infrastructure, making the transition to net zero more affordable and quicker to achieve than other low-carbon solutions, and will be significantly less disruptive for customers. Hydrogen-ready boilers cost around the same as current versions and can be converted to hydrogen in under an hour. The 4 distribution networks and National Grid are working together to deliver multiple hydrogen projects under the programme Gas Goes Green. The programme builds on the foundations of our existing world-class gas network through research and demonstration programmes applying engineering leadership, innovation and market know-how. H100 Fife is a key national project in this wider initiative to overcome the challenges and harness the opportunities of climate change in the most cost-effective and least disruptive way possible. Reducing carbon emissions and meeting our net zero target is one of the most significant challenges facing the UK and the whole world in decades to come. Delivering our 100% hydrogen network will be a big step towards meeting that global challenge, and it all starts here in Leavenmouth.
Okay, hopefully that came through okay for everyone. I muted myself halfway through because I didn't know if you were going to get repeated sounds, so hopefully you all got that. But just to recap the system that we're looking at here, this is what we refer to as an end-to-end demonstration. So we're looking at everything from the initial power generation through to the end user. So as the animation alluded to, we're looking at power generation for the hydrogen production system to incorporate offshore wind, which is taking offshore wind to produce hydrogen and then for the intended primary end use as for heat. We're also looking at an input from grid in the event that there is not sufficient wind energy to generate the hydrogen required in order to meet demand. But we are looking at electrolysis here, so of course it is green hydrogen that has already been covered in the definitions given earlier. We'll then have above ground storage on site in the form of 6 cylindrical steel storage tanks, which will be storing the hydrogen at 30 bar, and in order to ensure that security of supply, this has been sized to give 5 days of storage to give us that buffer in the event that there's no production. The hydrogen will then go through the necessary pressure reduction processes and also odorization using the same odorant, the primary odorant used by SGN and the other UK gas networks for that first point of detection. And our end goal here is distributing 100% hydrogen to initially 300 domestic customers, and this will be through a new network in parallel to the existing natural gas network, and I'll explain a little bit why that is in just a bit. So in terms of the sites that we're looking at, this is Energy Park Fife, which is located in Leavenmouth, an area on the east coast of Scotland. And this is really a community area that has been steeped in energy for decades, previously heavily involved in the mining industry, as well as coal export, then moving on to participate in the oil and gas sector with on-site fabrication of offshore structures, and in more recent years looking at offshore wind jacket foundation manufacturing. And as you can see there, you have OREX 7 megawatt offshore wind turbine, the Leavenmouth demonstrator turbine, which will form the offshore wind input for the H100 Fife demonstration. You can just see marked up there, you've got the orange site boundary, which is indicative of the site that we're looking at for the production and storage, as well as our demonstration zone. And then that is adjacent to the indicative hydrogen network area. This is really just a bit of an image to bring the project to life, some indicative visualizations that we've had done. We're still in pre-construction phase, but it gives you an idea of the components we're looking to have on site with the production facility and storage, and of course looking out to the turbine as well. So talking through some of the key principles for this project, this is where the customer comes into play, which is central to everything we're trying to achieve. And we're offering customers the opportunity to opt in for a hydrogen supply or remain with their existing natural gas supply. They'll also have the flexibility to switch between their suppliers, and those who agree to participate can also revert back to natural gas during the trial phase. And what this is all really aiming towards is generating key learning on attitudes towards hydrogen gas, which could help us to further understand the social acceptability of hydrogen and how people interact with it compared to natural gas and whether it's accepted. So the hydrogen demonstration facility that we're proposing as part of the H100 Fife site will be a key component of the customer engagement plan that will support this whole opt-in process. And this will be a facility with a central reception building and 2 demonstration show homes on either side, which will have equipped with hydrogen appliances. And what this really does is offers a place for customers to interact with hydrogen appliances in a home-like setting and really build their confidence in hydrogen, give them a chance to ask questions and learn about the project and what it can mean for them. So in terms of the customer value proposition that hydrogen affords, it's both low impact and low disruption when you compare it to other technologies. So as we've heard, hydrogen can offer a decarbonisation solution that's familiar. It mirrors interfaces of natural gas boilers. And with hydrogen, your wet central heating systems can be retained, and as well properties can be future-proofed for an energy transition by installing hydrogen-ready boilers that can operate on natural gas and then be converted over to hydrogen. So having a look at the regulatory model, we really want to ensure that we're making this easy and simple for a customer to be able to participate. And in that vein, we've developed a customer-centric regulatory model. And this really mirrors existing arrangements as closely as possible and avoids any complicated license exemptions or anything like that, which we're involved with as a gas transporter. And really importantly, we're ensuring it is cost neutral for the customer to participate. So the cost differential between hydrogen production and the natural gas sale price will be borne by the project. So this enables the project to sell hydrogen gas to an entry shipper at a natural gas price index. So this will mean that the increased cost of hydrogen production that is associated with an innovation demonstration of this kind will remain with the project upstream, protecting the overall retail supply chain and ultimately the end users. So the customer will pay the energy unit cost for natural gas for a hydrogen supply, and this is reflected in the customer bill. So overall, it's really about implementing that solution that is easy for the customer and has minimal administration for the retail supply chain as well in order to make it attractive. So just to go over some of the detail on the project structuring, as I've said, this is an SGN-led project, but we are working with the other gas distribution networks in partnership, as well as the appliance manufacturers associated with the High for Heat programme, so manufacturers of boilers, cookers and gas fires, which are all developed as hydrogen appliances. And in terms of where we are in the project phasing and staging, this is where it gets a little bit complicated, but bear with me. So this is all really driving towards being operational ahead of government heat policy decisions, which are widely expected in the mid-2020s. And we're looking at a 5-phased project, but everything that I've covered today in my presentation is all respective to phase 1, which is the 300 homes on hydrogen. But this is just to demonstrate that this is part of a much wider hydrogen programme for the area, where we look to increase the number of homes on hydrogen in phase 2 and also look at grid conversion rather than the parallel network. And also moving into industrial and commercial applications in phase 3, and also incorporating hydrogen transport. And it's all really building up to this phase 5, which is the whole system solution for the area. In terms of where we are now in the project, we've got stages that fall into phase 1. So where we are now is in stage 2. We're funded, the project development work is done, and now we've moved into the pre-construction phase. So undertaking a detailed design and really gearing up for the main construction window, which will be in 2022, all aiming towards having the first customers on hydrogen at the end of 2022, start of 2023. So overall, H100 Fife is really a critical demonstrator and evidence in the role that the gas networks can play in future energy systems. the opportunity for hydrogen production that offshore wind affords, and really how a transition to hydrogen can contribute to meeting net zero targets. And really this project with H1 and Fife is at the forefront of demonstrating a whole systems approach to decarbonisation. It's the way that it's got to be done. And it's bridging that gap between the electricity and the gas networks and bringing us together to achieve net zero. So that's the end of my presentation for now, but I'll be here for the Q&A at the end to answer any questions that you have. Thank you.
Lorna, thank you very much. That was fascinating. And yeah, please do get your thinking hats on for any questions. I see we've got one already, which we can come back to in the Q&A. So I'd like to invite Alistair McLean from the Ocean Energy Research Association to present now. So Alistair, if you want to come on and share your screen.
Sure thing. Thanks, Alex. So get yourself organized here. Okay, excellent. Listen, thank you very much, Alex, for inviting me along to speak a little bit about offshore wind from a Nova Scotia perspective. Certainly, I've enjoyed, Alex, your talk, Casper, and Lorna's. I think Nova Scotia, like North America, has a lot to learn from what you have already achieved in Scotland and in the UK. You all know that the offshore wind industry is sort of nascent and starting in the United States, and Nova Scotia, we're doing some research into understanding how we could help us on our path to net zero also. So OERA is, we're based in Nova Scotia, and I should say it, Nova Scotia is also known as Mi'kma'ki, which is the unceded traditional lands of the Mi'kmaq people. We are an independent not-for-profit research association. We're typically, over the past, have been focused on offshore energy, so geoscience for petroleum offshore research, tidal energy. We're now spending more time thinking about all energy questions related to the transition of an economy to net zero. And over the years, we've invested about $40 million into energy-related research. So Nova Scotia has some of the most aggressive greenhouse gas reduction targets in Canada. Our goal is to be at 53% of 2005 emissions by 2030, and then, like the UK, be at net zero by 2050. And as you can see on the chart here, we have a long way to go. And you can 15 megatons, 17 megatons thereabouts, and you can see the distribution of the carbon sources on the right there. Electricity, those will be being at 41%. Heat for buildings, which normally Nova Scotia would be from oil, but through the electrification of the grid as we move towards net zero, there'll be more electricity involved there as well. This is the current production of electricity in Nova Scotia, at least over the last 30 days, or recently in June. And you can see that wind, their overall 33% is from renewables. That's a combination of 19% from wind and hydro tidal being 11%. That's principally from hydro. There are no tidal energy turbines connected to the grid right now. And that wind is all onshore wind. Nova Scotia is blessed with a lot of space and some very good onshore wind resources. So there's approximately 500 megawatts of capacity of onshore wind in Nova Scotia today, and contributing, as you can see, to this date, this month here, about 20% of the total electricity. And because of the success Nova Scotia has had with onshore wind, generally, I think it's fair to say that people assume that if there's going to be more wind used in Nova Scotia, it would be onshore wind. But we've tried to do some work with some colleagues to understand, really, is that a good choice? When we think about some of the technology advancements that Alec talked about, with the size of the offshore turbines growing, so the capex per megawatt hour dropping, I think an analysis to understand, really, is offshore wind a good competitive choice, even in Nova Scotia, where there's more room for onshore wind? Let's have a look at that. So first, why do we even start thinking about Nova Scotia for offshore wind? This is a chart here from Agir, who presented this at a webinar that OERA ran last week. And simply put, you can see that the offshore wind resource in Nova Scotia is very good. The chart shows here it's certainly better than most jurisdictions in the United States, and perhaps most jurisdictions in the Western Hemisphere. So we're blessed with lots of wind. And the chart here is showing the technical potentials. There are 162 gigawatts of fixed bottom offshore wind and another 770 gigawatts or thereabouts of floating wind. So there's a massive opportunity here. One of the things which is quite interesting about the geography in Nova Scotia is in the top left here, where you see Sable Island. Sable Island is approximately 170 kilometers from the mainland of Nova Scotia. It looks like a very long sandbar, about 40, 50 kilometers long. The interesting thing there is that the water is shallow. As you can see there, it's 0 to 60 meters. There are significant surface area at Sable Island where the water depths are 0 to 30 meters. So it's this unique opportunity where there's tremendous wind resource being that far from shore, yet the water is shallow enough and the geology is quite good. So fixed bottom turbines are a realistic opportunity, provided one can overcome the technology hurdles of transporting electricity 170 kilometers to shore. So with that, again, the question I suggested we've been looking at Nova Scotia is how does offshore wind compare to onshore wind, where we have some success in Nova Scotia, have some space. So this is a curve that a colleague of mine, Sven Schultz, produced, which is showing an estimate of LCOE for offshore wind project at the Sable Island Bank. So again, this is approximately 170 kilometers offshore, but in shallow water. So fixed bottom turbines are possible. Moderate here refers to the case for a moderate cost reduction. We're using NREL data here, and we're comparing the class 5 to class 8. We're looking at different wind resources for onshore wind built in Nova Scotia. So the quick answer is here, you can see that by 2030 or thereabouts, offshore wind at the Sable Island Bank is comparable in price to onshore wind in Nova Scotia. So that was fair to say a bit of a surprise for quite a few people who've been thinking about this. And we know that LCOE is not the only thing we need to think about. Clearly, there's, as Casper talked about earlier, there's the balancing effects of intermittent resources and what's the cost of maintaining stability of the grid if you're looking at adding more intermittent resources, or in this case, wind. So this is a study that was performed by Lucas Swan and Nathaniel Pierre from Dalhousie University at the Renewable Energy Storage Lab, where they were looking at the Maritimes, the Eastern Canada, for a variety of criteria that could be used to choose where would one best build additional offshore wind resources and minimizing the cost for maintaining grid stability. So the layers you see here are shallow water depths, low correlation to existing onshore wind in Nova Scotia. So of course, if we want to build new resources, we don't want them being highly productive at the same time as existing resources, because that further exacerbates the stability question. Far better if we could have new resources producing slightly offset in time from the existing resources. We want a very good correlation with the load in Nova Scotia. In Nova Scotia, the load tends to be highest in the winter months. Not in the summer. We're temperate climate, so there's not a lot of air conditioning load, and the wind blows strongest in the winter, so there's a good correlation there. Time shift to existing Nova Scotia wind, which I've mentioned, and then a high capacity value. So when we add that all up, the graph shows the results here. We can draw a couple conclusions. Generally, adding more wind adding more onshore wind to existing onshore wind projects is going to exacerbate the need for further grid stability solutions. Therefore, if we put additional wind resources elsewhere, there's benefits to the stability to the grid. Two areas which are highly promising for Nova Scotia are in the southwest corner near the Bay of Fundy, and then also Sable Island Bank. So I think between the two studies, we see with the LCOE study that the cost of offshore wind is dropping rapidly, as we saw earlier. And so that's overcoming some biases, perhaps. Onshore wind will always be less expensive. And then this chart shows that in addition to that, particularly for thinking about domestic use of the energy from offshore wind, it has added value to the grid in terms of stability control. Now, the grid in Nova Scotia is fairly small, so let's say capacity around 1,500 megawatts. So if one wants to build a 1,000 megawatt offshore wind project, export energy, of course, is hugely important. From Nova Scotia's perspective, there really are two options. There's the export of electricity to the United States. So we are geographically quite close to very large markets like Massachusetts, New York, New Jersey. So are there opportunities for us to have improvements to the transmission grid so that offshore wind from Nova Scotia could be transferred down to the states, particularly probably to a state like Massachusetts. There are some significant challenges there. The existing transmission grid doesn't exist. And a Nova Scotia project would have to overcome some of the tax and procurement incentives which American states have put in place to encourage local development of offshore wind. The EU, Lorna gave an excellent discussion about hydrogen. Clearly, Nova Scotia is looking at that. Our understanding is that the EU will be able to fulfill its need for hydrogen until about 2030, but then demand's going to take off, and imports into the European Union for hydrogen is going to be an important solution to a net-free future for Europe. And Nova Scotia's got some significant benefits in that. We've got year-round ice-free ports, excellent renewable energy resources I've just shown. So we can certainly produce hydrogen at green hydrogen or zero carbon hydrogen at low cost, and the shipping distances are quite modest. So I think there's a really interesting future there for Nova Scotia and Atlantic Canada to be looking to the European Union as a market for hydrogen generated from offshore wind. So in summary, we see that offshore wind could be an interesting source of export revenue for Atlantic Canada. As I mentioned, Nova Scotia has very aggressive targets for greenhouse gas reduction. So, we're clearly on a path to net zero to attract industry. We have a offshore experienced workforce, very strong ties to the marine industry, but there's still some questions we need to answer. Where I've given a general overview of the resources around Nova Scotia, talked about Sable Island Bank, the Bay of Fundy. There's some more work done to understand where are areas suitable for offshore wind. Much of the work that the Electricity Catapult will understand, certainly. We need to look including at the environmental and ecological impacts of offshore wind. There's not really, that work's just starting. But we certainly see the potential for offshore wind and hydrogen, allowing Nova Scotia and Eastern Canada to be a green energy exporter. So there you are. If anybody has any questions about the thinking we're doing in Nova Scotia, or we're happy to hear good ideas, please send me an email. Thanks very much.
So that was fascinating. Thank you very much. And if I could invite Lorna and Casper to turn their cameras back on as well for some Q&A, that would be great. So we've got one question in the chat. So if you've got a question that you've been sitting on, please do continue to put them in. And I've got some questions as well. But to start with the question in the chat from Mick Dutton, and this was one for Lorna. So if customers can choose whether to opt in for hydrogen or remain using their natural gas, does that mean that some of the distribution infrastructure is duplicated, at least in the initial stages?
Yeah, absolutely, that's right. So we're building a new network in parallel to the infrastructure that's already in the ground distributing the natural gas. And our reason for that is we're not at a stage yet where hydrogen networks are mainstream technology that are being rolled out. So it is really, really key that we are able to validate that social acceptance and the attitudes towards hydrogen gas as an alternative to natural gas before we then mandate that customers convert from natural gas to hydrogen and we start to roll out hydrogen networks. So you're right in the instance that for this first phase of the trial, we are looking at a new network in parallel to the existing natural gas network, and that's really to support that opt-in optionality customer choice piece.
I think it came across really, really strongly in your presentation that the social aspects that SGN are considering are really close to the heart of the project, and that kind of demonstration site that people can go to seems kind of core to that. What are the differences that a customer might see when interacting with a hydrogen appliance versus a traditional natural gas appliance? Like, are they going to see anything different?
I mean, in terms of the interface, no, we don't expect that. We're working very closely with the appliance manufacturers in terms of how the flame looks compared to natural gas flame. It is really quite similar, and in terms of the controls and the functionality, that's all going to be exactly the same. The appliances are built to take up the same sort of dimensions within a property, and so it's not like you're looking to have a completely different space required for your hydrogen appliances. So from that side of things, it is really, really similar to what they already have, and that's what really empowers the move towards hydrogen, because it's what customers are used to. It's not a huge change from what they already interact with. One change that they might not visually see but experience is that if you're putting in new appliances to your properties, then you've always got that slight benefit of efficiency. So whilst under the project we're looking at a cost neutral model, so as not to incentivize participation, that allows us to maximize the social learning piece. But you know, customers may see that their home efficiencies are improved slightly because they're putting in new appliances, and that might have an indirect benefit on bills.
Oh, brilliant. And obviously a key part of the project as well is producing the hydrogen from an offshore wind turbine, in this case the Levermouth turbine. And you mentioned that you're going to have 5 days of storage kind of on site to kind of mitigate against in case there's a loss of production. Exactly. How much hydrogen does a 7 megawatt turbine produce if it's running at full whack?
So we've done a bit of profiling on the turbine there. We know that within an average year, we've got more than enough wind generation that we'd need to provide sufficient hydrogen for the properties. The storage system that we're looking at is around 5 tonnes, and that is sized according to the energy demand of 300 properties, to ensure that those properties would have a gas supply for those 5 days whilst production isn't happening. So the turbine that's there, we know we've got sufficient capacity, and that's to do above and beyond what we require for this first phase.
Great. And I guess, is there scope to expand that as well? I know that there's been a lot of work in Methil and Levermouth around kind of transport and kind of microgrids powered by hydrogen. You know, heat is obviously one aspect of our kind of future energy system. Are things like transport and hydrogen for those other use cases on the agenda as well within the H100 Fife project?
Yeah, absolutely. And we don't just want to stop at 300 properties. You know, that's the real benefit of hydrogen. It has an application in all of our energy sectors, and we know what its end use capability is. So we have a couple of major industrial users within the sort of immediate local area. We have Diageo as a distiller, which we could look at hydrogen supply solutions for. In terms of the transport side of things, we know that there's a new rail link being put into that area to connect up Fife to the Edinburgh Circle. You know, it's certainly not going to be a diesel train going in as a new line. It's probably going to be electric, but could we look at hydrogen applications for that and building a storage offtake for transport? There's also an existing hydrogen fleet in the area from a previous project. So we could look to provide a hydrogen supply solution for that transport fleet, and also looking at haulage and things too within that area. So we really are looking at the whole piece here. We're not going to stop at domestic. That's just the first phase, and then building it from there.
Oh, brilliant, thank you. Alistair, if I can turn to you as well to dive into a bit about what you talked about in your presentation. So you talked about potential offshore wind capacity for Nova Scotia of 776 gigawatts if you consider both fixed and floating, which is an enormous potential. I guess presumably that number is kind of before you've considered constraints like shipping lanes or other uses as the seabed and things. And that's kind of the maximum if you installed offshore wind across the whole area as a kind of carpet, if you like.
Yeah, you're quite right, Alex. It's just a technical capacity is there. There's work has started on trying to understand what are the prior uses, what are the constraints need to be taken into account, and so clearly that number is going to shrink quite a bit once we completed that work and done. Yeah, so I guess it'd be some marine spatial planning to understand really where would be some productive places to put some offshore wind.
But even so, when you consider it, when you compare it to I think 1,500 megawatts, so 1.5 gigawatt size of the Nova Scotian grid, you're still, you're swimming in energy effectively, which is a good position to be in.
Well, that's right. That's exactly it. And I mean, Atlantic Canada has had a history over the last 40 years or thereabouts of, looking for oil and gas reservoirs to be an exporter of energy. So, the purpose of this work was to show people that, we can continue to be thinking about being an exporter of energy because we have more than we need, and we have people not very far away who could benefit from it.
And I suppose to expand on that as well, Atlantic Canada is obviously quite blessed, but Canada's a really big country. How interconnected is the Nova Scotia grid with other provinces that you neighbour, or maybe even some of the more kind of landlocked provinces further away?
The transmission connection grid is weak. So that is one of the constraints right now that we would face. There is, hopefully there'll be some work to improve that over the next few years. It'll create an interesting market dynamic because Quebec, the first province outside of Atlantic Canada to the west, is rich in hydro. And they have been supplying, they've been exporting hydro energy to the United States for many, many years. So with an improved transmission connection, I think it's going to create a really dynamic marketplace for zero carbon electricity in Eastern North America.
And I think it's probably fair to say as well that Nova Scotia is leading probably the world in terms of its approach with other offshore energy solutions like tidal energy in particular. And can you comment on that approach that Nova Scotia is taking in general, not just looking at one energy source or another, but taking almost a portfolio approach to the energy sources featuring in your kind of grid mix?
Yeah, you're right. So Nova Scotia put in some really interesting policy, maybe 8 years ago, where recognized, I think like any jurisdiction, Nova Scotia looked at itself and said, what are the resources that we have here that could be interesting in the future? And how do we put policy in place to encourage industry to come and develop technology and see what they could do? And the tidal energy industry is a good example of that, where the province put in a feed-in tariff, which was quite rich compared to some of the contract for differences in the UK. And it's been quite successful in attracting developers from, quite largely from the broader UK. So there are a couple of Scottish companies, I think, poking around Nova Scotia, developing technologies in the tidal energy industry.
Sure.
Yeah. And it's an exciting time when you're developing technologies because you have some wins, you have successes, but you also have some painful lessons.
Mm-hmm.
But I think even there, Nova Scotia's done well to be able to understand that they understand that, and so therefore, when there are knocks, people just get back up and keep going, and we learn and we proceed. That's what's happening in tidal, and hopefully we'll see that happening offshore wind soon.
Yeah, I definitely think that's a lesson that we could learn from you in terms of our approach to